Functions combined with other functions? Functions inside other functions? Funkception. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking functions and combining them with other functions and seeing what happens. We can combine functions in various different ways, but let's start out with some simple ones to begin with. So for instance, I can always add and subtract functions. What that means is that if I take a function f, for instance, and subtract g function from it, what I'm doing is I'm taking the outputs of g and subtracting them from the outputs of f. Pretty straightforward, but that can come up with some interesting graphical representations. Check out this function here. F of x is equal to sine of x plus x. In this function, whatever the output of the trig function sine of x is, I'm going to add to that the output of the simple linear function x to it. This creates the interesting stepping behavior of this function. But maybe we can look at it like this. Remember that the standard form for the sine function is a sine of b times x minus h plus k. And remember that from this formulation, we find that the midline of the sine function is equivalent to y is equal to k. But in this combined function, sine of x plus x, the x function is kind of acting like the midline k, but instead of k being a constant, it's now a changing function, x. And just like the midline of the sine function is y is equal to k, now we have a midline y is equal to x. And indeed, if we superimpose the line y is equal to x on top of this combined function, we find that it does act like the midline of this function. What about this function here? F of x is equal to sine x minus cosine x. Well, in this case, it would be a little bit difficult to say that the cosine of x is acting like the midline or the mid-curve of the sine function. So instead, let's look at it a slightly different way. Again, we're going to subtract the outputs of the cosine function from the outputs of the sine function. So let's look at some important points for this function. So for instance, what happens at x is equal to 0? At x is equal to 0, the sine function is equal to 0, but the cosine function is equal to 1. So the value of the function at x is equal to 0 is -1. Let's look at some other important points as well. Where is this function at a maximum? Well, we might consider that the function is at a maximum when cosine is equal to 0, because it's going to subtract the least away from the sine function. But remember that the cosine function can also be negative when the sine function is positive. So when that is the case, the cosine function actually adds to the sine function here. The maximum then occurs where the sine function and the cosine function are equal in magnitude, but opposite in sign. That will be at points like 5 pi over 4, where the sine is equal to the square root of 2 over 2, but the cosine is equal to negative square root of 2 over 2. Adding those together, I get a maximum y value of the square root of 2. Likewise, the minimum value is going to be negative square root of 2. Okay, let's move on to multiplication and division. Multiplication is going to be the same sort of thing as addition and subtraction, where the product now of the outputs of the individual functions will be the final output of the combined function. But there are some other cool things that are going on here as well. So for instance, the multiplication really affects end behavior. So if I take this example here, x squared times e to the negative x power. I have a power function, x squared, and I have an exponential function, specifically exponential decay function. At large negative values of x, the power function here approaches positive infinity, as does the exponential decay function. If I go to negative infinity, the exponential decay function will also approach negative infinity. But as I go to positive infinity, bigger and bigger values of x, I find this result. The power function approaches positive infinity again because it's symmetric, but the exponential decay function goes to 0 as x approaches infinity. So we have conflicting end behaviors here. We have one part of the function that's going to positive infinity and one part of the function that's going to 0. And I can't just multiply those two things together, infinity times 0, to get some other value, which is the end behavior of the combined function. We could use some calculus to figure this out using the concept of limits, but let's just kind of use our intuition on this for now since we haven't gone over calculus yet. In this case, because the exponential decay function is a very fast function, as we've talked about before, and the power function, though fast, is not fast enough. So in this case, the exponential decay function overpowers the power function, and its end behavior is the one that is going to be dominant in this combined function. So the combined function, x squared times e to the negative x power, is going to approach 0 as x approaches positive infinity. Now, dividing functions we need to be a little bit careful about, because not only is the function defined by the constituent functions, but it's also defined by the fact that one of those functions, the function in the denominator, can sometimes be 0 potentially. So then we might get vertical asymptotes or other undefined terms in this combined function. So for instance, let's take a look at this function here, cosine of x over the natural log of x. We have a trigonometric function in the numerator and a logarithmic function in the denominator. So first of all, we see that it has properties of both of these functions. We have an oscillating behavior to this function, and we have an asymptotically decreasing behavior of this function, which we might expect from 1 over the natural log of x. Since the natural log of x grows to infinity, 1 over the natural log would decay to 0. We also see that because of the natural log function, this whole combined function is restricted to simply positive values of x. We can't put in any negative values for the natural log, and therefore the whole function, the whole combined function, is restricted to positive values for x. Now, interestingly, we don't have a vertical asymptote at 0 like we would for the natural log of x function. It's still undefined at 0, but we see that the function approaches 0 as x approaches 0 from the right. Again, we could use some calculus to determine this, but if we take a look at our graphing calculator or another graphing program and plot the point at what happens at x is equal to 0, we'll find that the y value is still undefined. Now let's take a look at the point x is equal to 1. Remember that at x is equal to 1, the natural logarithm is equal to 0, so therefore the denominator of this combined function is equal to 0, which isn't allowed, so we're going to have a vertical asymptote here. And also, because the natural logarithm crosses the x-axis at the point x is equal to 1, we would expect the combined function to have odd-like symmetry across that vertical asymptote boundary, as opposed to even symmetry, which would occur if the natural log bounced off the x-axis at that point. Furthermore, we have this oscillating behavior up and down, above and below the x-axis, and that is due to the cosine function here. But the amplitude of the cosine function we see diminishes to 0 as x increases to infinity. That's because the amplitude of this cosine function is analogous to 1 over the natural log of x, and that whole part of the function, 1 over natural log of x, decreases to 0 as x approaches infinity. So our last type of combining functions, compound functions. These are the type of functions where we have been using inverse functions in. So f of inverse f of x is equal to x. But we don't need to restrict compound functions just to inverse functions. We can compound any sort of function. In a compound function, I'm going to take the outputs of the inner function and make those the inputs of the outer function. So here we have the concept of an inside function and an outside function. And if I put f inside of g, that is going to be different in general from g inside of f. The time when they are equal is when they are inverse functions of each other, and both of these compound functions will be equal to x. Compound functions can be written in this way, f of g of x, which I've been using, but they can also be written in this way, f of x of g of x, the fog notation. And it's important to remember that compound functions can only exist on the intervals where both of the functions are valid. So if we take a look at a simple compound function like this one, f of x is equal to 1 over x, and g of x is equal to x squared plus 2x plus 1. If I write f of g of x, that would look like this, 1 over x squared plus 2x plus 1. If I did g of f of x, I'd get this result, 1 over x squared plus 2 times 1 over x plus 1. In both these cases, we've taken the output of the inner function and replaced it wherever we see x in the outer function. So for instance, with f of g of x, I've taken the output of the g function, x squared plus 2x plus 1, and inputted it into the input of the f function. So into the x, wherever we see x in the f function. So that gives us the result 1 over x squared plus 2x plus 1. So let's take a look at something a little bit more complex. For instance, f of x is equal to e to the x to the negative 1/3 power. Here we have a power function inside of an exponential function. So how does that affect things? In general, we need to consider the inside function before we consider the outside function. But in general, these functions will have properties of both of these functions. So if I take a look at the power function here, x to the negative 1/3 power, it looks like this. And we can see that we have a horizontal asymptote at y is equal to 0 and a vertical asymptote at x is equal to 0. So we know that the domain of this whole function must be restricted to values of x not equal to 0. Furthermore, as this function approaches positive infinity, I know that the power function approaches 0, but what happens to the outside exponential function? Well, as the power within the exponential function, which is the entirety of that inside function, x to the negative 1/3 power, well, as the exponent, whether it's a number or a function of an exponential function, approaches 0, the exponential function approaches 1. Because anything to the 0th power is equal to 1, including e. So this function actually approaches 1 as x approaches positive infinity. Same thing with negative infinity, because the power function has a horizontal asymptote as x approaches negative infinity of y is equal to 0. As x approaches negative infinity, the whole exponent of the exponential function approaches 0, and therefore the exponential function approaches 1. So for this compound function, we actually have a horizontal asymptote at y is equal to 1. What about at 0? Well, we can see that at 0, well, the power function is undefined. So we are going to get an undefined value for the whole compound function. And indeed, this function looks a little bit strange at around x is equal to 0. That's because these functions are doing two different things at x is equal to 0. The exponential function wants to go to 1, whereas the power function wants to go to either positive infinity or negative infinity, depending on whether we're approaching from the left or the right. So we get this kind of strange behavior here. Again, we can use some calculus to determine what these left-hand and right-hand limits would be. But for now, we can just say that the whole function is undefined at x is equal to 0. Let's look at the domain and range of this function. We see that the domain is all real numbers except for x is equal to 0. This is the same domain as the inner function, the power function. And if we look at the output or the range of this function, we see that the range is just from 0 to positive infinity, non-inclusive. Now, this pattern doesn't always hold, but generally we can start with the question, where are these functions restrictive in either their range or their domain, and how does that affect the compound function? For instance, the power function we know restricts the domain to all real numbers where x is not equal to 0. And the exponential function actually doesn't have a restricted domain. It exists on all real numbers. So combined, the whole compound function must be restricted to all real numbers where x is not equal to 0. In the next episode, we'll be taking a look at this problem. But in the meantime, why don't you try it out yourself? Take a look at this function. F of x is equal to x squared over sine of x. Now describe this function's behavior as having similar behavior to both the quadratic power function as well as the trigonometric function. Try it out yourself, and I'll see you in the solution.